Mathematicians are used to dealing with limits, but industrial vehicle manufacturer JCB wanted to push the limits to the extreme. They wanted to take their classic digger and turn it into the world's fastest diesel car. It was a seemingly impossible assignment, but a dedicated team of men and women, including engineering consultants from Ricardo, achieved astonishing success. This is the story of how maths made it happen.
My involvement in Dieselmax began when my boss called me in and said that we've got an interesting project opportunity here, and he described the fact that it was JCB looking to take the diesel land speed record, and I honestly thought it was a wind-up when he first told me about it, but you know, he was deadly serious, and we had 2 weeks starting that day to do the very first level feasibility study, which was to answer some key questions. How much power would it take to go 350 miles an hour? How many engines would it take to achieve that? And what were the critical vehicle constraints, vehicle mass, vehicle drag coefficient, frontal area, and so on. We probably didn't show it was feasible at that first stage. We showed that it would be very challenging, but I think the key thing was we understood what was important.
Who better to drive the car than Wing Commander Andy Green? Not only is he an RAF fighter pilot, but having broken the sound barrier driving the car Thrust SSC, he is the fastest man on Earth.
Thrust SSC and JCB Dieselmax challenging, exciting, very different ways. Thrust SSC solving the problem of what is the ultimate land speed record, trying to go supersonic. JCB Dieselmax is an entirely different challenge. We took 2 digger engines, put them in a car, and created the world's first 350 mile an hour diesel car. Even if Audi had taken their racing diesels, that would be quite impressive. For JCB to do that with the support of Ricardo and do it as a British project, taking digger engines, is truly astonishing. In some ways, more astonishing than what Thrust SSC did. Certainly from the engineering and the hardware point of view, it's quite extraordinary. How could that not be thrilling and exciting, particularly for myself as a fighter pilot proud of being British, as a mathematician who understands the challenges of the numbers to make that work? It was an extraordinary thing to be involved in.
If someone approached us and said we want to set the diesel land speed record, we wouldn't start with the JCB engine. Typically the JCB engine is what we call an off-highway engine. It's designed for products that aren't used on the road. It's designed for very long life, very high levels of durability, good levels of noise, low levels of emissions. It's really a very robust, high torque power unit. A race engine typically would have a large number of cylinders, maybe a V8, a V10, V12 engine, but we had just 4 cylinders. So the loads that we'd be putting on the systems, the piston, the crankshaft would be huge, and so we had to do a lot of modelling of how those loads would be managed and whether the structure of the engine itself would cope with this 6 times up rate in performance.
The unlimited record for a land speed record is a blank sheet of paper. You can power it with anything you want to. The aim is just to go faster than anyone else has. How do we take the limited power of 2 JCB engines and achieve the highest speed? So it's the problem's almost upside down. You're now given the limitations and find out what you can achieve within them. And of course, part of that was Ricardo's job in taking an engine and increasing its horsepower output by some 500%. Most people ask for 10 or 20% and feel quite pleased when they get it. 500% is an eye-opener. Using numbers, 200 bar of cylinder pressure, 6 bar of boost, pumping all 16 litres of oil through the engine, filters, the coolers, repressurising it, spraying it onto the back of the pistons every 5 seconds just to stop the pistons melting. And just to make it slightly harder, they've taken an engine that was built to work upright and laid it on its side. So a huge technical challenge. People who say British engineering technology is dead and you know, we might as well just let the Japanese make all our equipment from now on, I'm sorry, they're wrong.
It's when you have to push the design of something right to the limits. There is nothing to benchmark to start with, so you have to really do your analysis work to determine whether it's going to live. And the whole vehicle is only going to live as long as the components within it. So even if the smallest component in it happened to break, that's the whole thing broken because of that part. So everything has to be looked at. This picture here shows a connecting rod from the engine. The connecting rod is the part that joins the crankshaft to the piston. The piston is what compresses the gas and then under combustion that's forced, and then the force is transmitted via the connecting rod to the crankshaft in order to turn the crank and create the torque that's on the engine that ultimately drives the wheels. Now basically this rod is taken into a finite element package and loads are applied to it at the big end at the bottom where it connects to the crankshaft, and at the small end. Now these loads are derived from the gas pressure, and that's a compressive load that acts to compress that connecting rod. And then equally, the piston has a mass which needs to be accelerated up and down the cylinder, and this is another load that the connecting rod sees. It acts in the opposite direction at top dead centre when the piston is at peak compression. The mass of the piston is trying to stretch the rod. Through the analysis, the stresses are calculated, and the different colours in this picture are showing the different regions of high and low stress. The red areas showing regions of high stress, and blue areas regions of low stress. One of the key problems which was identified as a result of this analysis was the high stress at the small end oil feed. And as a result of the analysis, this oil feed was moved and placed at the bottom of the connecting rod, feeding through the rod, which gave a much lower peak stress level and made the part more durable.
Many of the components we used in the engine were standard production items, and it was a clear requirement from JCB that they should be standard. So when the man who drives a digger, a backhoe for a living, sees the Dieselmax, he can clearly see the engine that's in his digger is the engine in Dieselmax. They were modified internally, however, so where possible we removed unnecessary material to lighten it. We were always going to take the fully engineered approach and calculate everything before we went there and did it. We had to satisfy ourselves that it was safe and robust. The vehicle team spent a lot of time on that, using fluid dynamics to model the airflow around the car, and also then vehicle dynamics modelling to see how the suspension would behave. So we actually spent 8 months purely in simulation.
A lot of the time you have to write your own set of equations, or in some cases write your own short little programs. So this is an example of a series of equations we had to put together to calculate the bending moment on the shaft in the engine in order to determine whether it would be durable. Trigonometry is applied in order to resolve the loads into the perpendicular directions. And then the equations are assembled to work out the bending moment at every position along the shaft and at every speed that the shaft will run at. These equations are integrated to get the shaft deflections compared against what the bearing can take. You're able to look at how the shape of it changes as the shaft rotates, and you can look at this at various different speeds by changing the inputs at the beginning of the sheet. The actual result of the analysis was to choose to put 3 bearings in there instead of 2 that we just saw, which restrains the shaft better and reduces the peak deflections and the angular deflection at the bearings. A lot of the equations that are in this sheet, they're very simple. Differentiation, integration, things that you'll learn in secondary school, and engineering is learning how to apply that.
The car design process is long and protracted and involves a number of elements, and the drivability is part of it. It's not race driving, it's test and development flying on the ground. And that's something that, as a whole team, the engineers, the scientists, the materials specialist, the chief mechanic, and the driver all have to work as part of a team to understand what each other can and cannot achieve, so that as a group you have a workable plan to research and develop this car, not kill the driver, not destroy the car, particular favourites of mine actually, and actually achieve something which no one in history has achieved before. The driver has to be a key part of that. My enormous advantage in all of that process as a mathematician, fighter pilot first of all, but before even that, a mathematician, is being able to understand the science and the principles and a lot of the technology and the processes to make all of that happen. That gave me a unique advantage.
The driver was very, very important. Being someone who understands engineering, understands maths himself, he actually became far more part of the engineering team than just a driver. Very early on he got deeply involved in the project. He came to our technical engineering meetings to understand the work we were doing. He came and saw an engine running on a test bench to get a first feel of what he was taking on, sitting in between 2 of these engines producing this huge amount of power. Once we got into vehicle testing, It was really like having another form of data recorder in the vehicle. We had control systems which would log lots of temperature sensors, motion sensors, all the critical control parameters, but we also had Andy Green's commentary that explained what we were seeing in the data. At the end of a run, we'd pull the data up on a big screen, lots and lots of charts, and Andy could get straight into that data, talk through it with us, and it was far quicker for us to get that kind of understanding of what we were looking at, having a technical guy at the wheel, feeling things as they were going on and having a grasp of what all the systems around him were doing.
One of the big perception problems about not just mathematics but the whole science, technology, engineering side is that it's very much a boys' preserve. It's all about cars and aeroplanes and science and spanners and it's boys' stuff, and it's really not. The majority of the people out there, the majority of the people you see working on it are because that's what society expects. But they really shouldn't. Extreme examples of being fundamental to the whole of the team in Thrust SSC. The run controller, the person to whom everybody else on the desert spoke. 30-odd people out there, 4 different radio frequencies, me being one of those speaking elements. We're all talking to one person who's controlling 200 square miles of desert, plus the airspace over it with our spotter aircraft. And she is actually using the science of airspace and ground space management to make all of that work. Fundamental to doing it safely and having people in the right place at the right time. Jump forward 8 years to JCB Diesel Max. A young girl in her 20s, graduate, motorsport experienced. She programmed and looked after all of the systems in the car, including the 2 flat screen displays I had in the cockpit. When we had an engine problem and couldn't get both engines to work together, we identified a different way of doing it. I needed more information in the cockpit. She brought out a laptop, typed into it for 10 minutes, and some new displays appeared that I used directly to get the engines on boost. She was pivotal to that. We could not have done it without her. I cannot understand when a 12-year-old schoolgirl looks at people like that. They couldn't see that engineering and science and maths aren't interested, or there isn't a place for them, because there really is.
I think you need a very logical approach. A good level of common sense is always very valuable, and a good understanding of basic engineering fundamentals. So the maths that goes with that is a critical essential, because for me, the maths I learnt at school, and the more and more I've got into engineering, all of a sudden I've found how that's absolutely critical for a lot of what we do day to day. I enjoy the fact that it's always another challenge. Every project we have is different, and the challenge is just get it moving on and on. We have to continually develop new solutions, new technologies to achieve these requirements.
This is Malcolm Campbell, 1933, Bluebird on Daytona Beach. He was the fastest man on the planet that day, doing things with cars, engines, technology, aerodynamics that no one had ever done before. 6 years later, that expertise was going to finish up in various different ways, building a whole generation of equipment that the UK and the Allies were going to need for the Second World War. Thereafter, elements of the same concept moved forward to building jet fighters, building the Apollo space program, building computers. Let's just find out what is actually possible given where technology is today. The British have done that with the land speed record incredibly well. What we need to do is take that culture and get it out to absolutely everywhere, so that we don't look back and say, well, we invented the Spitfire, the Harrier, the world's first supersonic airline, the Concorde, but we don't do that anymore. Yes, we do. We really can, and we really should. We should be getting our school kids proud and excited about the chance to join in.
Personally, it was a brilliant project, my best project experience of my life. Biggest engineering challenge, biggest team challenge, and to be involved to the level I was and pulling the Ricardo team together that at the end of the day would deliver the engines that powered the vehicle to 350 miles an hour was just a fantastic experience. Very, very hard work. All the team worked extremely hard the last few months of the project. There were very few days off, many long working days, but all our strengths and skills across the team came together ultimately to deliver the engine performance on the day that got us the 350 mile an hour target.
Perhaps the most remarkable bit of the story, I had to throttle back to about half throttle at 350 miles an hour because the car was still accelerating so hard. Suddenly we're looking at a car that has so much more to give